Swayam Prabha. Digital India. Educated India.
Welcome to the organ printing course. In the last couple of lectures, we have discussed various 3D bioprinting techniques like inkjet based bioprinting technique, extrusion based bioprinting technique. So in this lecture, we'll discuss another type of bioprinting technique, that is laser assisted bioprinting or LAB technique. So this technology is also called lift because here the principle of this technology is laser induced forward transfer. So we'll see what are the different components of this laser assisted bioprinter and how does this technology work. So the first, let's start with what are the different components of a laser assisted bioprinting setup. So if you can see in this image, there are at least 4 different components of a laser assisted bioprinting techniques. Like the first is the laser source. A laser source is being used here for doing this forward transfer, where so first a laser source is used. So with the help of laser source, we are transferring the material from the donor to the collecting. So here there is a donor layer. So that donor layer consists of a laser transparent. Basically this is a ribbon. So this ribbon has also 3 layers. The first top layer is the glass layer. So the glass layer, and it is a transparent layer so that the laser can pass through this transparent layer. And then below that glass we have a energy absorbing layer that is made up of either gold or any other material. And then below that energy absorbing layer we have this bio ink. So the bio ink is also can be made up either with it's a cell laden hydrogel. Sometimes other biomolecules like growth factors, cytokines and other bioactive factors can also be included or encapsulated within this bioink material. So bioink is nothing but a cell laden hydrogel, right? As we have discussed in the earlier bioprinting, like extrusion based bioprinting technology also. And then also this ribbon has to be made all the time fresh before the bioprinting process. Now when this, so that now here after this, whenever the laser is striking the ribbon passing, then it can pass through the gold, it can pass through the glass layer, that is the transparent layer, and hitting the energy absorbing layer or gold layer, so that gold layer can absorb the energy, and then the bio ink layer is there below this, and then this thing. So now in this technology laser assisted bioprinting technique also is a contact based approach, because here nowhere this donor layer and the collecting layer or the substrate, they are coming in contact with each other. Never they come in contact with each other, neither they come in contact through the materials also. So that's why this is a non-contact based approach, and this can be it has some advantage because of this non-contact nature. The other important properties of this bioprinter is this is also a nozzle free approach. As you can see here, there is no nozzles or syringes attached here or involved here, so that's why this is a nozzle free approach. Unlike extrusion based bioprinting or inkjet based bioprinting, in both these technologies we have seen that how a nozzle is being used for bioprinting process, where we move the material through the nozzle and or extrude the thing. In case of extrusion based printing, we extrude the material through the nozzle so that the material comes out in the filament, then we can plot them. In inkjet based bioprinting also, you have seen there is a nozzle attached to that printhead, and then where through the nozzles the droplets are generated, right? But in this case also the droplets are generated, but there is no nozzle involved. So it's a nozzle free approach. And due to this thing, due to the non-nozzle free approach and non-contact based approach, there are advantages. We will discuss this in the later. what are the different advantages because of this thing. But please remember, so this is the main component of a laser assisted bioprinting setup is the laser, the ribbon, print ribbon, and then the collecting plate. And the print ribbon, again, it consists of, the first layer is the glass or transparent layer, that is made up of glass. Energy absorbing layer may be made up of gold, and the bioink layer where the cells can also be involved. So the layer of biological material can also be there, like cells and hydrogel. And then a substrate or collector slide that is placed on a motorized stage. Right? Now this here the moving part is mostly the laser that can move on the top surface of this, on the surface of this gold, and then it can move so that whenever it moves to the, whenever it is hitting the ribbon, passing through the glass side, and it can hit the energy absorbing layer. Right? So this is the whole setup of a laser assisted bioprinting setup. Now let us see the operation of this technique. As I have already discussed, a laser source is used, and then that laser is focused on the ribbon or the print ribbon, where we have this print ribbon. As I have already discussed, the print ribbon made up of, first layer is the glass layer, then below that there is an energy absorbing layer, and then below that there is a bioink layer. Now wherever the laser irradiates on the ribbon, it can pass through the transparent glass layer, right? So, and then it can hit the energy absorbing layer. So passing through the glass layer, it hits, the laser hits the energy absorbing layer, and in this case, whenever it hits the energy absorbing layer, that layer, it absorbs the energy from the laser and it hits up. So the purpose of this energy absorbing layer is to absorb the laser energy and hitting up, right? So whenever it hits up, then what will happen? Then this, as we have discussed in our thermal based inkjet printing, that whenever there is a hot surface touching to the bioink or cellular hydrogel aqueous layer, then what will happen? A bubble will be produced, right? So that's also, in this case also, air bubbles are produced whenever this laser hitting the energy absorbing layer, and the energy, whenever it hits up, that time the air bubble will be produced. Now whenever there is a air bubble produced within this, in between this energy absorbing layer and the bioink layer, so it creates a high gas pressure, right? So the bubble, whenever there is a bubble produced, that bubble creates a high gas pressure. So due to this high gas pressure, what will happen? It will propel a droplet of the cell-laden bioink, or it will dislodge the cell-laden bioink from that bioink layer, and that droplet will be collected or to be transferred to the substrate or print bed, right? So this is the whole operation of this of this laser assisted bioprinting. Again, I am summarizing the operation, where a laser source is used. That laser source irradiates the transparent glass layer, and then passing through the transparent glass layer, it hits the energy absorbing layer, and whenever it hits the energy absorbing layer, it basically, the energy absorbing layer, it hits up, right? That hits up because of this, the energy that is transferred from the laser to the laser layer. Now because of this, now when the energy absorbing layer hits up, and because it is touching that aqueous cell-laden hydrogel or the bioink, so a bubble will be produced, right? So because of these bubbles are produced, that bubble, that creates a high gas pressure between this layer. So because of this high gas pressure, a droplet from the cell-laden bioink, droplets will be generated, and that droplets will propel. So that high pressure gas pressure that propel the droplet from the ribbon to the collecting plate. So that means it transfers the droplet from the donor plate, that is the ribbon, to the collecting plate, and where actually it is getting deposited. Now whenever I am moving the laser on the top surface of this glass layer, it is, whenever it is hitting the energy absorber, from there a droplet will be generated. So if I move to the next spot, from there again another droplet will be generated. So like this, I can as per our design, I can move the laser on the glass surface, and from different areas of this ribbon, the droplets will be generated, and then that will be deposited on the collecting plate. So in this process, basically this process works on the principle of droplets production. So whenever the droplets are produced, those droplets I can basically pattern on the substrate as per the design, and I can create any kind of pattern or any kind of design that is required. This technology has got huge advantage because of this, as I discussed, because of this nozzle free and non-contact based approach, and also because of the droplets, and because we are using lasers. So depending upon the laser spot size, the droplets can be generated, the very fine droplets can be generated. Even droplets containing single cells can also be generated with this process. So that is the biggest advantage of this laser assisted bioprinting technique. Now, depending upon the type of laser used, or depending upon the setting of the system, like this thing, there are different types of laser assisted bioprinting setups are there. The very first one is the standard laser induced forward transfer, or whatever we have discussed laser bioprinting setup. Like the first is laser induced forward transfer. As we have discussed, with the help of laser, we are transferring the material from the ribbon or donor plate to the collecting plate, right? So that's process is laser induced forward transfer. In this case, a very fine layer of that energy absorbing layer or metal layer is used, right? So there is some concerns that the laser can actually get can pass through the metal layer and can hit the also the hydrogel or the bioink layer, right? So if the laser hits the bioink layer, then it can cause damage to the cells, right? So that is the concern in case of laser induced forward transfer. So that concern is addressed in the second technique, that is absorbing film assisted laser induced forward transfer, or alpha lift, right? In this case, the difference is here a thick sacrificial metal layer, that is the second, that energy absorbing layer. So here that is a thick one, thicker than the layer that is used in case of laser lift, right? So a thicker 100 micron, almost 100 nanometer sacrificial metal layer is there below the glass layer. So that acts as a laser transparent layer, or that acts as a energy absorbing layer in this case. So that is the only difference between alpha lift and LIFT. So please remember that in the case of alpha lift, a thicker sacrificial metal layer is used. In case of late lift, a less than 100 nanometer energy absorbing layer or metal layer is used, right? Now the next technique is, another version is the biological laser printing. So this is also called BioLP. So it is a modified version of the alpha lift, like this other technology. And here what is being used here, a CCD camera is used to focus the laser radiation, right? So in this case, this works on here the resolution is higher than the other technique. Here, because of this CCD camera is used to focus the laser radiation, so that a very fine laser spot can be created on the glass surface, and then that spot can be, so the energy absorbing layer, that spot of energy absorbing layer can be heated up, and then a very fine droplets, the size of droplet can be generated, and that can be transferred to the layer. So this is the difference between BioLP and the alpha lift. Now, but in this case, like LIF lift, alpha lift, or BioLP, in all these three techniques, a high power laser is involved, and because of that, there are concerns that this laser, if this high power laser can get pass through the metal layer, and it can hit the bioink layer. If the bioink layer that comes in contact with the laser, then there can be a damage to the cells, that because the cells are encapsulated in the bioink layer, so the cells can get damaged due to this laser irradiation. So that's why there are this another development from this this laser assisted bioprinting techniques are the matrix assisted pulse laser evaporation direct write. So this is also called Maple DW, right? So here the difference is, in this case, in this technique, a low power laser is used, right? And that low power laser is either in the UV or near UV wavelength that is being used in this case, right? Right. So one concern of using high power laser, that is eliminated here in this technique. So we here they use, one generally use low power laser. So low power laser is being used, and other difference is the that metal layer that is present in between the glass and the bi-wing, that is the transparent layer, laser transparent layer, and the bi-wing. Here a biopolymer layer is being used as a absorbing energy absorbing layer instead of metals, right? So in the other technique, as I have seen, we have seen that the lift or the alpha lift or bio-LP here, where metal energy absorbing layer is used, but in case of Maple DW, a biopolymer based energy absorbing layer is used. So the advantage here is, whenever, because now here one thing is low power laser is being used. So low power laser, whenever it is passing through the transparent glass layer, hitting the biopolymer energy absorbing layer. So the biopolymer energy absorbing layer that is heated up, and then a bubble is created, a bubble is formed, and that because of the bubble, a high pressure gas is created. So that high pressure gas propel the bioink or cellular hydrogen that is present below that energy absorbing biopolymer layer, and then from there a droplets will be generated, and droplets will be generated, and those droplets can be transferred to the cell. So this is the difference between Maple DW and the other three techniques. Now there is a further development here, where the laser guided direct writing is another type of laser assisted bioprinting, where generally a weakly focused around 800 nanometer laser is being used. Right? So the difference here, in the other technique, mostly either UV or near UV laser is used, and then also metal layers are there, and then metal layer is there in the other three technique. In Maple W, energy absorbing biopolymer layer is here, but here the laser beam is used to move the cells in a liquid suspension. So here the working principle is different than the other techniques. Here mostly the laser beam is used, and that laser beam also 800 nanometer laser beam is used, and that is used to move the cells in a liquid suspension. Mostly the cells are there in the cell media, and with the help of laser we can move them, and then we can print them together. We can print them, or we can combine them. So and we can pattern the cells with the help of this laser guided direct writing, or LGDW. Another important feature of this thing is the laser beam is coupled with the hollow optical fibers. So through the optical fibers, the laser beam is transferred to the liquid suspense media. So here, because of this, the working distance actually increases from 300 micron, because 300 micron to several millimeters. So that's an advantage of this LGDW. So here we have discussed different types of laser assisted bioprinting techniques, starting with lift. Lift is the most common one, and that is the conventional laser assisted bioprinting, where, as I have already discussed, it has the standard format of this thing, like the standard ribbons consisting of glass layer, energy absorbing metal layer, and then bio-ink layer. But in this case, the glass layer is finer. In case of alpha lift, the glass layer is thicker, almost close to 100 nanometer, and the advantage is it can block the laser, so that it prevents the laser passing to the bio-ink layer. In case of bio-LP, it's a slight modified version. Here we use a CCD camera to focus the laser radiation. In case of matrix assisted pulse laser evaporation direct write, or Maple DW, here a low power laser is used. Other advantage, other difference is that here a energy absorbing biopolymer layer is used for transferring energy to the material. And in case of LGDW, a weakly focused LG 800 nanometer laser is being used that can move the cells in the liquid suspension. And also, the optical fiber is used for transferring the laser to the. Now, let us discuss the advantages of this thing. As I have already discussed, because this process is a non-contact based process, okay, so that's why here the post printing cell viability is very good in this case, because this is a non-contact based method and we are generating droplets. So due to the droplets, the cells are transferred from one place to another place. That's why the uh, it has got huge advantage in terms of cell viability because of this non-contact process, and also it's a nozzle free approach. So that's why also the cell viability is very good. One another advantage of this technology, because it's a nozzle free approach. And as we have discussed, in case of inkjet based bioprinting and extrusion based bioprinting, so there are problems of nozzle clogging, so that is also eliminated in this case. So the nozzle clogging problem is also eliminated. Other than that, this process is high resolution, because here the droplets are generated and we can create very fine droplets depending upon the laser spot size and the process. We can create very fine droplets. Even single cells per droplet can also be a possibility. So that's why, so with single cell basically we can so in this technology the capabilities of printing single cells, and that single cells, if we can print it that droplets containing single cells, then we can create a very fine structure having high resolution structures can be possible. Another capability of the printing high cell densities, because if we can also this is it offer 10 to the power 8 cells per ml also we can use in this technique, right? So because what you can do, the high cell density, the cell, when we are loading the cell or encapsulating the cells in the hydrogel, their high cell number can be loaded within this biwing, and that can be coated on the below the energy absorbing layer, and then whenever there is a, and then that can be used as the ribbon, and then we can do the bioprinting process. Other thing is low viscous cell suspension can also be used in this case, like 1 to 300 MPa per second. So that is like that kind of low viscous suspension can also be used in this case. Right? And another advantage of this technique is the high resolution cell patterning, because as I discussed that in this case we can create very fine droplets, and then so that we can create the pattern the cells in a on the stage as per our design. So multicellular microenvironment, so basically we can create a multicellular microenvironment very well create because of this capability of patterning the cells in a high resolution manner. So these are the advantage of this laser assisted bioprinting technique. But there are certain challenges associated with this technique, like the risk of laser exposure. As we have discussed, that whenever the laser is striking the ribbon, passing through the glass, hitting the energy absorbing layer or the metal layer. So, but sometimes if the metal layer is not too thick, the laser can pass through the bionic layer also. And if the laser is passed through the bionic, so that can expose, so that cells can get exposed to the laser, and that can cause damage to the cells. So, and because of that, photonic cell damage can happen. So the cells can get damaged because of this laser exposure, and due to this, that can be an adverse effect, and the cell viability can be an issue if there is a laser exposure to the cells. Other than this, because of uses of metals as a energy absorbing layer, that metallic nanoparticles can be produced due to this laser irradiation. Thus, these nanoparticles, if the nanoparticles are produced towards this biowing site, and then the biowing can get contaminated with these nanoparticles, so that can cause cytotoxicity, because these nanoparticles can induce cytotoxicity. So that is very true in case of lift and upper lift, because in both the case the metal energy absorbing layer is used. Okay, so in this case, this is the concern that metal nanoparticle can be there. Other challenge associated with this technique is the scalability. Now, because this technique, the droplets are produced, right? So when the droplets are produced, with these droplets, we can create very fine structure. We can create with high resolution structure. We can create. But suppose our interest is to print centimeters level, centimeter size tissue, then there is a challenge. So with this technique, it's very difficult to fabricate a tissue with higher dimension, like centimeter size tissue can be permanent. Other things, suppose we want to print multiple tissue at the same time, then also the scalability is a major issue here in this technique. The other challenging part is because the ribbon has to be fabricated all the time. Fresh ribbon has to be fabricated, so that can be an issue. So that ribbon, so we have to produce this ribbon all the time. So after every layer, because the ribbon changes after every layer, so that's why that can be another challenge thing. Other than this kind of system, the laser assisted bioprinting system is a costly system, because the high cost of the laser systems and also the process is also very expensive. So the high cost of the laser system, due to the high cost of the laser systems and other parts of the bioprinter, these printers are expensive. The other thing is the complexity of controlling the laser pulses. How do you control the laser pulses and all these things? That also can be challenging. Like all other bioprinting techniques, here also there are certain process parameters that we need to optimize, and I have been saying this for different printing techniques, that before even if you start doing any bioprinting, you need to optimize the process parameters. And then different process parameters are like some laser related parameters like laser intensity, spot size, pulse, and pulse duration. So mostly the pulse lasers is used for this in case of laser assisted bioprinting. So the intensity of the laser is an important factor, because if your intensity is very high, then the bioink can get damaged due to this thing. If the intensity is too low, then the droplets will not be transferred. So you need to optimize this laser intensity. Another thing, spot size. Suppose spot size dictates the resolution of the printed droplets. Right? So in case if the spot size is very fine, we can create very fine droplets. If the spot size is higher, more, then the droplet size will be more. Laser pulse, how for pulse durations like this. So how often this laser should be irradiated, that is, so the pulse of the laser, that is laser pulse, is important, and also the pulse duration, how frequently or what is the duration of this thing, that is very important. Other than this, the viscosity of the material or viscosity of the hydrogel, cell laden hydrogel, the bioink, is another important factor, because if the viscosity is very high, then the droplets transfer will not be effective. If the viscosity is very low, then it will not stay under the ribbon. It will just start dripping by itself. So we want a viscosity that is, but in this case, low to moderate viscous bioink can be very well used. Surface tension of the bioink is another factor, because the surface tension of the bioink, that will hold up the bioink together. So whenever there is this laser is on, it is by high pressure gas is generated. That time only the droplets will be transferred. So surface tension is another important factor of the bioink. Cell density, as I have already mentioned, high cell density definitely can be used. So depending upon the application, you can choose a particular cell density, and that is like that is also a process parameter. Another process parameter is the distance between the ribbon and the collecting stage. Generally these two are kept very close to each other, so that distance is also what will happen if the distance is more, the droplets are generated, and droplets, if they have to pass a air gap before even reaching to the stage, right? So the droplets, that distance also you need to optimize. And the other thing is the depth of the ribbon. How deep, what is the depth of the ribbon, that is important, because if you create the more depth, like if the bioink layer is thicker, then also it can cause disturbance in the droplet generation and droplet transfer. So that there is ribbon depth of the ribbon also you need to optimize. Now next thing is where exactly this this laser assisted bioprinting being applied. So there are various applications where this technology is applied. The very first is the tissue engineering, and we have earlier discussed tissue is nothing but where we can create artificial tissues for repair or regeneration of the diseased or damaged tissue. So here in this case, this laser assisted bioprinting technique has already been demonstrated for fabricating cornea and skin tissues, and there are also other tissues also being targeted with this bioprinting setup. In case of cornea, the corneal keratocyte cells are encapsulated in a hydrogel like alginate and other hydrogel, and then this process they are coated in the under the rib as a ribbon, under the metallic energy absorbing layer, and then this process then the laser is on. The process, as I have discussed, the laser is on, and then the droplets are generated. So these corneal specific keratocyte cells, those can be actually plotted on a on the collecting plate, and then definitely we can then a cornea matrix like structure can be generated out of this. So this can be used for tissue engineering of this thing. Other things, this a skin is for by fabricating up skin tissue construct, also this kind of laser assisted bioprinting technique has been already used. Now another application of this technology is to generate in vitro tissue and organ models, and we have seen that in our earlier lecture also we have discussed this, that if we can create a tissue or organ that is mimicking the native tissue and organ, if we can recreate that kind of complexity, the microenvironment of that particular tissue, then that can be used as a model, a physical model of that particular tissue and organ, and then that kind of models has various applications like for fundamental study, as a model for drug screening like drug and toxicity screening, and also there are other applications. The other research area is the or application is the cancer model, where with the use of cancer cells we can encapsulate these cancer cells within our bioink or the hydrogel, and then actually using this process laser assisted bioprinting or laser is induced forward transfer, we can get the droplets containing these cancer cells, and that can be plotted on the print stage. So various types of geometry or various types of microenvironment we can do, cancer microenvironment we can create, and then we can actually work on this different, or we can work on different cancer modeling development, like we can work on different types of cancer like breast cancer, glioblastoma model, esophageal cancer model, even different types of other types of cancer model can be created with this kind of process, with this kind of bioprinting process, and then that can be of use. So thank you everyone. We come to the end of this lecture. We will again meet in the next lecture. Thank you very much for your listening.